let's have a look at how we deal with chords with parametric equations, in particular chords of parabolas. Now, we start with letting these 2 points be on the parabola. So put them anywhere you like. 2AP, AP squared, I've put it there. 2AQ, AQ squared, we've put it over this side. Doesn't matter really, they could be on the same side if they like. It's a little bit easier to show if they're like that. Now we want to draw a chord between those two. What does that look like? Well, we just draw a line between them. So we call that a chord. So remember, a chord is a line that goes from one point of a curve to another. Pretty easy. So if we want to find the gradient of this chord, well, we're going to use our gradient formula. y2 minus y1, x2 minus x1. So if we use our coordinates, we get AP squared minus AQ squared over 2AP minus 2AQ, which when we do the difference of two squares, do a factorization here, we get to cancel the P minus Q, and we cancel our A's as well. It just gets us P plus Q over 2. So there's our gradient of our chord, and that will basically be the parametric values summed and divided by 2. That's how we can do that. How do we find the equation of that chord? Well, again, we're going to use our y minus y1 equals m outside of x minus x1. So I've chosen the point 2AP, AP squared. You could have chosen 2AQ, AQ squared. That would still work. So what happens is that we start to expand it out. So P plus Q on 2 times x, and the P plus Q on 2 times 2APQ gives us AP squared minus APQ, and the 2's can cancel. So we have a look here, we can cancel the AP squared on both sides from that, and we get y is equal to P plus Q on 2 times x minus APQ. There's the equation of your chord, and that'll be a straight line going between the two chords. So it's pretty easy to use our parametric forms and our values, and then just use our all the equations we used in coordinate geometry. So the mathematics isn't really new in that regard. So one of the interesting results that comes up, if we know it's a focal chord, now a focal chord is a special type of chord because it goes through the focus. So it must pass through 0a, because the parabola is x squared minus 4ay. Now if that's the case and we substitute 0a into this equation, then let's see what happens. Well, we get y is equal to a, x is equal to 0. So on this equation, then we must have a being equal to minus APQ, because this part is 0, so we get rid of it, and we get minus APQ, and thus if we do a cancellation here of the minus of the a and divide by minus 1, we get the result that PQ is equal to minus 1. So there's a result that we need to remember, and really, well, suppose you don't really have to remember it. You should be able to prove that every time. That once you get the equation of your focal chord, that you can know how to show that if it's a focal chord, then the product of the parameters is equal to minus 1. So then that's how we prove it. We just substitute 0a in there, because that's the parabola it's sitting on. So a question here, we've got a chord joining the parameters 2 and minus a half on the parabola defined by x is equal to 6t and y is equal to 3t squared. So if that's the case, well, when t is equal to 2, what's our x values? Well, it would be x is equal to 12, y is equal to 12. So that would signify the point 12, 12. So the parametric value of 2 gives us the Cartesian coordinates of 12, 12 on the parabola. And I know it's going to be a parabola because that follows the definition of a parabola in a parametric form. So I've got one point there. I'm going to use my gradient by this idea, because we just saw that if we've got two values and we want to find the equation of the chord, the gradient of the chord is the sum of the two parameters divided by 2. So we do the sum there. Remember, x is 1's equal to q was minus a half. So if we take q to be minus a half, 2 minus a half over 2 gives us 3/4. So if that's the case, we've got our point, we've got our gradient. So even though we got it through our parametric points, we're using a Cartesian point here. then we get, it doesn't really matter, we just do it our value of our gradient. So we multiplied through by 4 and then collected our terms, and we get 3x minus 4y plus 12 equals 0 is the coordinates of the chord. This is the equation of the chord on that for that parabola. Find the Cartesian equation of the parabola. Well, if you remember from what we did earlier on, to find the Cartesian equation, we put our parameter t there in terms of x. So t equals x on 6, and then do our substitution. So we get the equation x squared is equal to 12y. What's the coordinates of the focus? Well, from that, 4a would equal 12, or a is equal to 3. So the vertex is 0, 0, s is equal to 0, 3. So now we can look at, show by substitution that part A is a focal chord. Well, we get 2 times the half is equal to minus 1, which should work. It worked. If it's going to be a focal chord, that would be the case. In terms of the substitution, though, we should really take our equation, 3x minus 4y plus 12. So let's write that down. 3x minus 4y plus 12. And we want to take our coordinates of our focus, which is 0, 3. And if we can sub it in, it should calculate to 0 for us. So 3 lots of 0 minus 4 lots of 3 plus 12 equals 0. So we get minus 12 plus 12 equals 0. So yeah, that's true. 0 equals 0. So it's true. So it is a focal chord because we can show it there, but also we can prove it because we know that situation. So the 2 times the minus a half will give us minus 1. So we have that result. The parameters values multiply to give us minus 1 for that focal chord. The focal chord that it sits on, those 2 values, must be a focal chord. So there we go. That's how we're going to start to use the idea of the focal chord and the chords in our problems on parametrics with a parabola.